Hi, everybody. So this is our first video about the content, the theoretical content of our course. And I think it's a good way to start to talk a little bit about how you write math. And this is going to be brief. It's far from being comprehensive. And it's going to be basically describing a particular example of a mathematical statement, very similar to one of the assignments in the homework assignment number 1. So you can see a little bit of the structure of a proof. And some of you and most of you have seen proofs by induction, either in linear algebra 271 to 72 or math 220, the introduction to mathematical reasoning and proof, or somewhere else. So this is just going to be a very quick reminder of an example of a proof by induction, by mathematical induction, just to give you a sense of the expectations on how to write proofs. And we will work on our proof writing during the semester, so it's totally okay if you feel a little bit not used to the way that we write proofs, or maybe you have not seen them in a while, or you feel that you need a little bit extra practice. So that's why we are here. So we are gonna be working on proofs. So this is example. It's a very known example. Is about a proof. So we're gonna prove that the following identity is true. So we are gonna prove that 1 square plus 2 square plus ... n square is n times n plus 1 times 2n plus 1 divided by 6. And for n being a natural number and greater or equal than 1. So this is a prototypical example of a type of statement that we can prove using mathematical induction. So the way that I would write my proof is I will structure it. And one thing that I do, just for my own sake, I will put in parentheses what is the method that I'm going to be using. So proof by mathematical induction. And what I also do is I say mathematical induction on what. So when you have a statement in which you are using induction is a process, is an algorithm that requires an input. So in this case, it's a natural input is n. So mathematical induction on n. And when you write induction, in my way of thinking about induction, looks like a train that has some wagons, and those wagons are connected one with each other. The first wagon is what I would call the base case. So when you have a base case in induction, it refers to the initial wagon. In this case will be n equals 1, because that's prescribed by the problem. And you have sometimes to keep an eye on what would be the natural base case for your induction. In this case, it's a natural choice. We say base case n equals 1. And what we do when we have the base case is just verify that the equation actually holds. So when n equals 1, 1 squared is equal to 1. But on the other hand, 1 is equal to 1 times 1 plus 1. I'm just plugging in the value of n. 2 times 1 plus 1. And I'm dividing by 6. And I just do the algebra. 1 times 2 times 3 divided by 6 equals 1. So we just verify that 1 is equal to 1, which I hope it brings you joy. It brings me a lot of joy to know that we managed to check the base case. So that's the first step in mathematical induction. The next step when you write a proof by induction is the induction hypothesis. What is the induction hypothesis? You are making an assumption. So you assume that in this case this is an equality, right? So we have an equation so that the equality holds. And I will write it down. It doesn't hurt. And I will use a counter. You can use another letter just to kind of have a difference between the n, that this is for all n, or you can just say that it was for some. So my particular preference, I say 1 squared plus 2 squared plus dot plus k squared equals k plus 1 2k plus 1 divided by 6 for some k in the set of natural numbers k greater or equal than 1. So I'm just using that auxiliary variable, so to speak, to jump from one wagon to the other. So I'm jumping from the k wagon to the k plus 1 wagon. So now what I call the inductive step is we can continue the narrative of our proof. So now we are assuming that this holds. So I should say assume that the equality holds for some k natural number greater or equal than 1. And the inductive step is, well, adding k plus 1 squared, because that's the jump that we want to do. We want to jump from the k wagon to the k plus 1 wagon using logical and correct mathematical steps. So you can add to an equality the same quantity in both sides, and it's going to be the same value of truth. So it's still going to be a correct statement. So adding k plus 1 squared to both sides of the equation. And here is a suggestion that mathematicians use all the time, and I encourage you to do. You can label your equations. If you have a proof that has 4 equations or 4 statements, you could definitely label them, and that's totally fine. You can call them, I will call this one, for example, equation 1. So you can just say of the equation of the equation 1. So then we continue with the narrative. So we say adding k plus 1 squared to both sides of the equation 1, we get, and we do algebra, so we get 1 squared plus 2 squared plus the dot plus k squared plus k plus 1 squared, right? So that's basically just adding that term to both sides. And I'm using the induction hypothesis to conclude that I still have this term, and I'm just simply adding k plus 1 squared. And the good thing is now we really hope, cross our fingers, that the algebra is going to help us, and hopefully it does. So I see here that there is a k plus 1 and there's a k plus 1 squared. So those two really want to be factored. So I will factor the k plus 1. And that's good news because that's the next step, right? I'm trying to jump to the next wagon. So I really need something that depends on k plus 1. So far so good, looks excellent, promising. And then I factor the k that stayed in that side of the term. Then you get the 2k plus 1 divided by 6. Oops, like that. Plus, and then 1 of the k plus 1. So, right? And then you continue to the algebra. I encourage you to be organized, and the grader and the instructor will thank you for being organized and clear and clean with your justifications. So we have k plus 1 times, and you get k 2k plus 1 plus 6 times k plus 1 divided by 6. And then you say, okay, what's going on here? Well, so far we just try to do some algebra, right? So we will get 2k squared plus, then you get the k times 1, and then you get the 6k plus the 6k plus 6. So then you put them together, you get 7k plus, and then there's another term that is 6. And then you realize, okay, what can I do with that? Well, you go back to your algebra class and your algebra memories, and then you say, okay, the k plus 1 stays like that. Let me just maybe write it in the other line, so it's still having the same structure, k plus 1. And then here you factor. There's gonna be I need to get a 6 in the final term of the polynomial, and there is a 2k, so that suggests there will be a 2k plus something times k plus something else. And then you realize that you get a k plus 2 and 2k plus 3 divided by 6. And you verify, that's important, verify that you get the same expression. You get 2k squared, which is this one. Then you get 4k plus 3k, 7k, fantastic. 3 times 2, 6, kaboom, fantastic. We can continue. Now, what I will do is I do a little bit of cleanup of the expression. I say k plus 1, that's the first term, times. I will flip these 2k plus 3 and k plus 2 because I wanted to be in the same form of the original formula. I will put k plus 1 times. And then this one has a nice way to write it down. So it becomes 2k plus 1. Remember that that's the goal at hand. That we jump from the k wagon to the k plus 1 wagon. So everything has to be written in the k plus 1 language. So this is victory, because remember, we had this formula 1. So you have k plus 1 to k plus 1 divided by 6. And now the formula became 1 squared plus 2 squared plus k plus 1 squared is k plus 1 plus 1 2k plus 1 divided by 6. So we succeeded in changing k, and it got transformed into k plus 1. So, and then the conclusion, it's like writing an essay, right? Like you have the punchline is the inductive step, and now the conclusion, I will just maybe write it like this. At some point, you could remove these headings, the conclusion or the inductive step, but it helps me to differentiate the different steps of the proof. The conclusion is by PMI, and this reads the principle of mathematical induction. The equality holds for all n in the natural numbers n greater than 1. And I don't know about you, but I get very excited to choose the way that I finish my proof. I use a little box. That's one way. If you feel more comfortable, you can remove it and write Q E D quod eram demonstradum. That's Latin for I'm done, and what's next. Alrighty, I think that's all. So if you have any questions about this proof, office hours is a great place, or just ask questions during class, or talk to your math fellows. And I'll see you soon. Take care.